So I think everyone saw this sentence by now. So this sentence has basically at least two problems. The first one, it's scary if you're not a math junkie. And the second one, it's true. A monad is a monoid in the category and the factors. So, but today I don't want to talk about category theory or things like that. I want to face monads through a more practical approach. There's this thread, maybe someone read it, from Bonnie Eyes. I mean, I hope her last name, I read it correctly. So she says basically that she works for Twitter, and she's been writing code in Scala for 2 years. But she was at the Scala conference. I heard monad, monoid, free monad. To make a long story short, she says, do these things are really useful in practice? So the subject of this talk is, I hope I will try to show that are really useful in practice. So very common answers for what a monad is are effects. Now, if you don't know what they are, what the experts are talking about, everyone will think side effects. It's not only about side effects. It's effects, they mean something else. Another common answer is sequencing, like Daniela showed you how to sequence monadic functions. So this time, in this talk, instead, I want to show that you can use monads to write more polymorphic functions. So they can help you raise the abstraction level. Sorry for the wave, but in my version, there is not that wave. Okay. So anyway, like Linus Torvalds said, talk is cheap, show me the code. Let's take something concrete. An advertising, a very simplified subset of an advertising service. You have keywords. We are in Italy, so keywords like carbonara, matriciana, and so on, linked to a restaurant or a gym. Anyway, and the match type. Anyway, don't worry about this model, because when you talk about monads, about these functional programming patterns, one of the advantage of them is that they let you not care about the concrete type they're dealing with. So when experts say algebra, they mean just that. They mean you talk in math, in algebra, you talk about operations and laws that behind those operations. So you're not interested in the concrete number you're dealing with. You know, in algebra, monoid, a monoid, you know that there are you have the zero and the append and the associative law. What the concrete type you're dealing with, you're not interested. So we have a couple of type aliases. So a keyword is a list of keywords, and a result is an either string or an A. Okay. You have this concept that is a keyword expander. Keyword expander is just a function from keywords to future keywords, because basically maybe you're using a service, so you don't want to block. And you know, you have this keyword expander, and you have the two basic plans, for example, two advertising plans, basic plans and advanced. You know, you have these two advertisers, one that pay more and one that pay less. So there will be many keyword expanders, and you have the necessity to reduce a list of keyword expanders. So the first attempt is, okay, I'll write a function that takes a list of functions from keywords to future keywords and an initial value, and I will produce a future keywords. So what will you use to reduce a list? A fold over the list. So this is the implementation. Okay, this works. Let's see, usage. Okay, you have a keyword, a list of keyword expanders, and you reduce that list. Nothing to tell home about. What's the problem with this particular implementation? Let's see it again. As I said before, if you see the implementation, there's no reference to keywords. I don't use the concept, the keyword concept in the implementation anywhere. So we can write a more abstract version of this function that will work with more cases than a list of monadic. Sorry, didn't want to say monadic. A list of, of functions from keywords to future keywords. Okay. So this is the improved version. The name changed from fold future keyword to fold future. We don't care about the particular object we're dealing with. And the implementation is exactly the same. I didn't change anything, just used the parametric polymorphism to make it more reusable. Okay, so suppose there is another business necessity, and you have this concept of keyword validator, which is just a function that go from keywords to result keywords. Okay, again, we will have a list of this function, and we will have to reduce them. And this is the implementation. As you can see, this time I had to help the Scala compiler, because otherwise it would, if you see the first section of for the left, I gave a hint, a type hint to the Scala compiler, otherwise it would infer right as the type, and it wouldn't have worked. So it's just a detail. But let's see the usage of this function. Again, you have a list of validators, and you reduce it using this function, fold either. So again, there's a problem here. The problem is this one. There are repetitions in those two implementations. Let's see what means something to be repeated. The code between the double stars is the only part that is different between the two implementations. So the name, okay, we can in some way fix this. The result of the function within the list, and the global result of the method. Yes, and one more thing is the zero for the left. The value we're passing to the first section of for the left. You see, future.successful, and right in it in the second implementation. So, is there anything that will let me factor out this repetition? Okay. Some type theory, nothing to be scared of. Okay, this morning Miles talked about star, arrow, star. It meant this part here. So, in type theory, you have simple type, which is int, string, double, and so on. And then unary type constructor, which is a type which expects another type to be constructed, like list, option. You say list or what? So it expects another type. The concept extends to binary type constructor, like either or function one and so on. They expect two types in order to be finally constructed. And then our friend, higher kind of types. Higher kind of types is a type that abstract over a type constructor. In this case, a unary type constructor, but you can also abstract over binary type constructor and so on. So this is all the theory of the talk. So yeah, we're over. Okay, and this is the concept of monad for developers. You can take two routes. The one from category theory, which is really interesting, and I advise you to have a look at it. But if you don't want to go that way, you can just stick to this definition. Really, a monad is just a higher candidate type, which abstracts over a unary type constructor, and has just two primitive methods. Pure is sometimes called unit, but anyway, the concept is this one. And flat map. With these two functions, you can write a lot of other derived functions. So a monad is a very powerful concept. Okay. So that's what I said. It's a type class that it's polymorphic over a unary type constructor, two abstract methods, and this one, the monad instances must respect some laws. At this stage of things, you can postpone looking at these laws, because I advise you, of course, to write your type class in terms of functor, monad, and so on. But at the end of the day, when you have a good grasp of these concepts, I suggest you use some library that already deals with verifying laws for the instances and so on, like Hkts, or if you prefer scala-z. I generally use Hkts because it's more intuitive for me. I can guess the imports by selectively. Instead, with scala-z, I go by import scala-z lowercase, import scala-z uppercase with the first letter. So you import everything inside. Anyway, back to our repeated code. Okay, let's see how monads can help us factor out this code. Okay, we already said that the repeated code is the one between the double star. Okay, we can find a common name, easy. And we have to abstract over a unary type constructor, because future and result, which is a type alias of either string A, are unary type constructor. Well, either would be a binary type constructor, but I partially applied string, so it's a unary type constructor. So by abstracting over a unary type constructor, and by putting a constraint that says, okay, M is a unary type constructor, but there must be an instance of monad for that type constructor. From now on, I will say that list is a monad, option is a monad. Whenever it's not precisely correct, whenever I say list is a monad, rewrite as there is an instance of monad for list, okay? And this is just a version that will work with any instance of monad already written and that has already that must yet be written. So it's code that will work with future code. You have the advantage of reasoning only with one function, instead of having we saw that we had to implement this function for future, for either, but for any type, any unary type constructor that has an instance of monad. So this way, you have just one implementation to reason about. Okay, let's give it a spin. Okay, we have our keyword expanders, which was a list of functions, now I can say it, of monadic functions from keywords, future keywords, a list of keyword validators, and we reduce it by using our brand new function we have here. Okay, it works. We could go for the aperitivo because we're over. But can we do better? I mean, let's see it again. There's just one more thing that we can abstract over. This function will only work with lists. But the only method we're using from list is for the left. So the first thing that comes to our mind is, let me see which is the superclass of lists where for the left is defined. So this is the first thing that comes to your mind. Okay. Okay. So just look at the class hierarchy and see what's the base class where for the left is defined. It turns out to be gen traversable ones. So we replace list with gen traversable ones, and this version will work with list, with vector, and with any child or subchild of gen traversable ones. But can we do even better? Before I said that this version will work with any subclass of gen traversable ones. Subclass. What a bad word that is. Yeah? Okay, we can do better. We can do better. What was the mistake I made? The mistake was that I opted for subtype polymorphism instead of parametric and ad hoc one. I mean, I wondered, I asked myself, what's the superclass where for the left is defined? Okay? The right question would have been, what's the type class where for the left is defined? Does such a type class exist? Well, there is the foldable concept, basically. Yep, it's foldable. You can find it in Hkts. So we can write our final version by taking out the gen traversable ones and using f. F is a unary type constructor, again, and the constraint is that there is an instance of foldable for f. One of the advantages of this version is that it will work also for, it will let you reduce also option of that function, because option is not in the collection hierarchy, but there is an instance of foldable for option. So if you have an option of a function that goes from A to future A, or an option of a function that goes from A to either string A, you can keep using this function to reduce that function. Did I say function? Yeah, function. Okay. So this is the final version, really, and it's simple. It's really simple to reason about once you have a good grasp of this concept. Really, it's beautiful. The type signature is almost bigger than the implementation. The signature of the function is almost bigger than the implementation, really. But anyway, simple is different than easy. The first time, I've been programming in Java for 15 years. I started programming, I've been programming in Scala only for 4 years. I can remember that when I started studying these things, it was hard for anyone. Don't think that people like Miles Sabin or anyone already knew these things right from the start. They studied these things, and of course they are ahead of us, because I can remember finding a post by Miles Sabin that he wrote in 2011. I didn't even know that existed Scala in 2011. And the post was, if I can remember correctly, unboxed union types through the Kerry-Harvard isomorphism. I read it at the beginning of my Scala study, and, well, I went Control W and Control say, okay, let's see in a couple of years. Then, to tell the truth, I read it again last year and still didn't understand. No, I understood. This time I understood it. It was crystal clear. It was crystal clear because I studied a lot and I could understand what Miles wrote in 2011. So, anyway, the takeaways from this talk are monads are practically useful because you wrote one function instead of n function, and where n is the number of different monads, okay? So when people say, hey, Java has monads, it's not totally true, because if maybe it's true, in my opinion, if I cannot abstract over monads, you don't have monads. That's why when people say Kotlin, I say higher kind types or GTFO. That's my. So yeah, monads are practically useful. Don't let the buzzword scare you. As I said, I had to study a lot to understand these things. But now you have something that in return. Because I wrote this function right from the start. I didn't start writing for the future keywords. When I had to write this function for futures, I said, no, I will write something that will work for any monads. When you're in trouble, always follow the types, because they tell you the truth. So, that's all I have for today. If you have any question. Thank you.